My name is Ying Shan. I'm going to present deep crossing. This is a joint work with my colleagues at Microsoft Bing and Microsoft Research. Thank you. And this is agenda, the list of things that I'm going to walk you through in my presentation. Since I'm the only person standing between you and the lunch, I'm not going to go line by line of these and just skip to the next slide. The motivation of our work is to build a web scale model for applications such as web search, online advertising, and so on. These applications usually have billions of samples, and they have multiple heterogeneous features with hundreds of thousands of millions of dimensions. And depending on the applications, they usually require various types of object functions, be it regression, classification, ranking, and so on. So this work is in the specific context of Bing ads. When a query is sent to the Bing search engine, in this case, Microsoft Surface Book, we sometimes return back a few ads alongside of the organic results. And in this case, the ad has ad title, this doesn't work. The ads have a ad title, ad description, and there is also a bidding keywords which is provided by advertisers, which is sort of play an important role connecting query and ads. And once you click on an ad, it will send you to a landing page. So this is a very rich problem space. And one of the central problems is given a query, how likely a user will click on ads. And we will use this problem to demonstrate the capability of deep crossing. And to address a problem like this, common approach is to manually create combinatorial features, which is defined in the joint space of individual features. And these combinatorial features are sometimes called cross features. And then once you have these features, you feed the features into a suitable trainer. But the challenge is usually what and how many features to cross. Do I have to cross query and add a title, query and description, or query cross with add a title, cross with landing page? So this is where our scientists and engineers spend most time on. And you can see that the combinatorial features, because of this nature, is very expensive to create, to maintain, and to improve. Think about someone in this company. He has created dozens of combinatorial features, and if someday he leaves the company and the one takes over his work, will have lots of hard time to understand, first of all, understand his creation, and then improve on it. So this is a lot of work. Also, it's very hard to get help from others. If they want to help you, they have to learn your domain knowledge first, and this doesn't scale. So the question is really, can deep learning help? By looking at a single neuron, in this case, a sigmoid function with two inputs and two weights. And you just do a simple Taylor expansion, and you can immediately see that inside the circles, red circles, these are the cross terms. And this of course, is not the full theory of deep learning. But imagine millions of them stacking together in the deep layers. The richness of interactions it can capture among the individual features. The essence of deep crossing solution is to use features as raw as possible and let deep neural network take care of the rest. And we all know the same strategy works for image and speech recognition. And we'll see how it works for in our context. These are the examples of individual features. For text input, such as query, keywords, and a title, we convert them into so-called trilettergrams, which is an invention from researchers at the Microsoft Research in Li Deng's team. Each of these features has around 50,000 dimensions. We also use one hot features for match type, a feature like match type, which is a categorical feature, and also ID features, such as campaign ID. And we also use conventional dense vectors to represent campaign ID count, which is a counting feature in numerical counting feature in 5 dimensions. And this is what we meant by heterogeneous features. Each feature has different kind of nature. This is the model architecture of the deep crossing. On the bottom are the multiple input features of various kinds, as we have seen in the previous slides. And each raw feature has a corresponding embedding layer, which is mapping from the raw feature space to a small embedding space. And as you can imagine that if the raw feature is already in a low dimensional space, we can skip this step. The key difference here, when you compare the embedding layer here with things like word2vec, etc., is that the embedding process is an integral part of the overall optimization process. So when you have the embedding layers, there is a stacking layer, which is simply concatenating all the layers into a single vector. And then the output of the single vector will be passed on to a cascade of residual units. We'll explain later. And the output of the last unit, residual unit, is going to provide the input of the last 2 layers, which are the scoring layer and the objective functions. And as we expected, this objective function enables regression, classification, and ranking. Now, for implementation, we use open source tool called CNTK. I'm sure some of you have attended their hands-on tutorial yesterday. It's a deep learning tool set that take care of the details such as SGD, the overall SGD, the gradient computation, the switching between GPU and CPU matrix computation. And it also has high-level modeling languages such as NDL, branch script, and Python binding, which is coming soon. On the right, I'm showing the core of deep crossing model in NDL. And as you can see, the entire model is only a little over a dozen of lines of scripts. So it's the implementation in this framework is pretty simple. Now we do the same thing for the residual unit, which we borrow from the residual network for image recognition, which beat the world record. And what we found is that the using of residual unit give us very good convergence property, and also additional control to prevent overfitting. And on the right side are the macros we use to represent the residual unit as a part of the deep crossing model. These are the data set we use to train and evaluate deep crossing. The rows column is the number of samples in millions, and the rows dims is the total input dimensions in thousands. And we have CP1 and CP2, which are the 2 types of click prediction tasks. And you can see that both the number of samples and the total dimension can be quite high. And using the data in the previous slides, we built three models. The first model is built for CPU1 tasks. And we allowed only 2 text input, in this case, query and keywords. And we compare deep crossing with DSSM. And DSSM model is created by Microsoft Research. Is an excellent model specialized in handling a pair of text input. And in this case, both on the small data set and the big data set, deep crossing is outperforming DSSM. And for Model 2, which is built for CP2 tasks, we still use 2 input, which is query and edit description. And we compare deep crossing with DSSM and our production model. So again, deep crossing is performing better than DSSM, but it's worse than our production model, which is expected because the production model in this case is using much more features. The Model 3 is a full-fledged model for CPU1 task. We use 12 layers of the network, 31 individual features, and we train it on 2.2 billion samples using 32 GPUs on our own GPU cluster. And you can see deep crossing model is performing better than our production in this case. So a question that I get a lot from the post-presentation was where are the cross features? And the answer is that the cross features are implicit. It's really, they're encoded in the parameters inside the red circles, which is the deep layers. Now the question is, when can deep crossing help you? There are 2 scenarios. One scenario is when you are building a model from scratch for a new application domain. Deep crossing is usually very good at build a high-performance model with a fraction of efforts. And the comparison is at the scale of between many years versus a few months. The second scenario is when you are looking for new directions to improve existing model. The chances that deep crossing can still give you a significant boost in performance as we demonstrate in our experiments. So how to actually build deep crossing? There are 5 steps. For the first step, the bad news is that you still have to put some efforts into collecting your own feature. This step you cannot skip. But the good news is that you don't have to worry about the cross feature. That will save you a lot of time. The second step is a modeling step. You can use the deep crossing model template we put onto the CNTK wiki page. And you can download this template and connect the model with your features. And that's pretty much what you do. Sometimes you have to do a little bit of tuning, but this is it should be fairly easy. And the training phase, the training time varies depending on the size of your data and the complexity of your network. The basic assumption here is that you have one or several machines with a few GPUs on it. Of course, you have to do evaluation, and you have to iterate and tune some hyperparameters in this case. And the time will vary. But based on our own experience, the deep crossing model is quite robust in a sense that you don't really need to tune many parameters. Usually, you just do a few try on the learning rate, and it will work for you. in terms of deployment, you can use CNTK. CNTK has an eval DL module with free MKL library. So the thing is that how easy this can be incorporated into your serving stack, and whether the runtime will be within your latency constraint also depends on your application. So the conclusion here is that deep crossing is a dummy model for web scale application. It's really simple to implement, and we have tested on a number of different kind of data, and it all give us state-of-art performance with a fraction of efforts. And for future work, we'd like to extend deep crossing for more applications. One example is to do the fusion of text, speech, and image signals. And there are also lots of room to improve on the model itself. For example, we can incorporate LSTM into the deep crossing, and we can use sequence-based embedding, which is more powerful. And of course, we welcome any kind of your feedback. Feedback include you are so excited about our data, our platform, our tools, and our problem space, and you would like to be part of us. Thank you very much.
Okay, thank you very much for this very concise and actually very overview and nice talk. Any questions here so far? I know everybody wants to go to lunch, so we'll keep it brief.
Do we have to use the sigmoid activation function? You said in the Tanner expansion, it has to involve the cross, or we can use other continuous ones, right?
Yes. Oh, so the question is, do we have to use sigmoid? Sigmoid was just an illustration example. Actually, in our deep crossing, we use ReLU all the time. Yeah. So as long as it's a nonlinear function, you will keep this Taylor expansion property, and you will be fine. Yeah.
Any other questions?
Hi, a quick question. I think one of the motivations that you mentioned for not having the explicit cross was to have an easy handover, or like people can understand without the domain knowledge. But do you think like the deep crossing, which to me seems like more like a black box, will be easier for doing this task?
Yeah. So I think that's a very good question. So in terms of interpretability, the neural networks is notorious laid bad. But in terms of having other people helping you, this is actually good because I'll give you an example. We developed this model, and we are facing a problem when we put it onto multiple GPU. The performance is not as good as running on one GPU. So our MSR colleague at the same time, they develop a model averaging algorithm, which actually can fix that problem. So we just grab that algorithm and put it into our model, and it works just beautifully. So those people, those MSR people, they actually don't have any knowledge of our domain. Right? They know nothing about the ads, they know nothing about the search. They just know how to do better model averaging, and it just works for us. So this is what I meant by scale by getting help from others.
Okay, makes a lot of sense.
Thank you, Rich.
Okay, well then let's thank the speaker again. And
thank you very much.
Enjoy your lunch.